From aerial photography to emergency response, modern drones are reshaping our world. But have you ever wondered what's packed inside these sophisticated flying robots? Today we're going under the hood to explore the intricate technology that powers these unmanned aerial vehicles and the complex rules we're building to manage our increasingly crowded skies. It's a story of miniature brains, superhuman senses, and the quest to build a new kind of air traffic control. At the absolute heart of every drone is the flight controller. Think of it as the drone's central nervous system and brain, all crammed onto a tiny circuit board. This is the component that orchestrates every single aspect of flight. Its primary job is to keep the drone stable. To do this, it relies on a constant stream of data from its onboard sensors, especially gyroscopes and accelerometers. The gyroscopes measure how fast the drone is rotating on any axis, while the accelerometers measure its linear movement. The flight controller's software runs complex algorithms, processing this data hundreds of times per second. If it detects the slightest deviation from the desired orientation, say from a gust of wind, it instantly calculates the necessary correction and sends signals to the electronic speed controllers, or ESCs. Each ESC then precisely adjusts the speed of its corresponding motor. This constant, high-speed feedback loop is what allows a four-propeller quadcopter to hover perfectly still or execute sharp, agile maneuvers. But the flight controller is more than just a stabilizer. It also manages telemetry, sending crucial data like altitude, speed, GPS location, and, most importantly, battery status, back to the pilot on the ground. To perform these complex tasks, a drone needs to perceive its environment. This is where a sophisticated array of sensors comes in, acting as the drone's eyes and ears. The most fundamental are the navigational and stability sensors we just mentioned, which are usually combined into a single package called an inertial measurement unit, or IMU. For outdoor flight, the IMU works hand-in-hand with a global navigation satellite system, or GNSS receiver. We all know its most famous variant, GPS, but modern receivers also connect to other constellations like Russia's GLONASS, Europe's Galileo, and China's Beidou for increased accuracy. This satellite link is what enables most of the autonomous features we take for granted, from pre-programmed waypoint missions to the life-saving return to home function that automatically brings the drone back if it loses signal or the battery runs low. Beyond just knowing where it is, a modern drone needs to know what's around it. This is where obstacle avoidance sensors become critical. These systems use a variety of technologies. Ultrasonic sensors, much like bats, emit high-frequency sound waves and measure the echo to detect large, nearby objects, which is especially useful for maintaining altitude close to the ground. Infrared sensors emit beams of infrared light to spot obstacles, even in low-light conditions. But the real game changers are LiDAR and vision sensors. LiDAR, which stands for Light Detection and Ranging, uses laser pulses to create incredibly accurate 3D maps of the environment. It's the gold standard for precise obstacle avoidance and navigating through complex spaces like forests or construction sites. Vision sensors, which are essentially smart cameras, use advanced image processing algorithms to not just see an obstacle but to identify and track it, allowing the drone to navigate intelligently around moving objects. Finally, we have the payload sensors. These are the sensors that perform the actual mission. The most common is a high-definition or 4K camera for photography and videography, but payloads can get far more specialized. Thermal cameras detect heat signatures, making them invaluable for search and rescue teams looking for a lost hiker at night, or for inspectors checking a building for heat loss. In agriculture, drones equipped with multispectral sensors can analyze light reflected from crops across different parts of the electromagnetic spectrum. This allows a farmer to assess crop health, identify irrigation problems, and spot disease long before it's visible to the human eye. All this amazing technology is useless if the drone can't talk to its operator. This is the job of the communication system, or data link. For most consumer and commercial drones, this link is achieved using radio frequency, or RF, transmitters and receivers, typically operating in the 2.4 or 5.8 GHz bands. These offer a good balance of range and data throughput for sending control commands to the drone and receiving a live video feed and telemetry data back. For long-range missions that go beyond the pilot's visual line of sight, drones can use satellite communications, or SATCOM. This allows a drone to be controlled from anywhere in the world, with signals relayed through orbiting satellites. Increasingly, however, drones are connecting via cellular networks. The widespread availability of 4G and especially 5G offers a high-bandwidth, low-latency connection that's perfect for streaming high-quality video and transmitting massive datasets in real time, especially in urban areas. Of course, to fly, you need thrust. In a multi-rotor drone, the propulsion system consists of three key parts: brushless motors, propellers, and the electronic speed controllers we touched on earlier. Modern drones exclusively use brushless motors because they are more efficient, more durable, and offer a much better power-to-weight ratio than older brushed designs. The propellers are the drone's wings, designed with a specific length and pitch to generate lift, and the ESCs act as the middlemen, translating the low-power commands from the flight controller into the high-power electricity needed to spin the motors at precisely the right speed. All of this is powered by a battery, which is often the single biggest limiting factor in a drone's performance. Most drones use lithium polymer or LiPo batteries, prized for their ability to deliver a lot of power quickly in a lightweight package. The central challenge in drone design is balancing battery capacity with weight. A bigger battery means a longer flight time, but it also means more weight, which requires more power to lift, creating a cycle of diminishing returns. To manage this precious resource, modern drone batteries contain a sophisticated battery management system, or BMS. This onboard circuit is the battery's guardian, constantly monitoring voltage, current, and temperature. It protects against overcharging, over-discharging, and overheating, all of which can damage the battery and create a safety risk. The BMS also provides the pilot with an accurate estimate of the remaining flight time, which is absolutely critical information. With all this sophisticated technology packed into increasingly accessible devices, a new challenge has emerged. How do we regulate them? How do we safely integrate millions of flying robots into an airspace already used by planes and helicopters? This has led to a complex and rapidly evolving web of regulations around the world. In the United States, the Federal Aviation Administration, or FAA, sets the rules. They make a distinction between recreational and commercial use. If you're flying for fun, you need to register any drone over 250 grams, pass a simple online safety test called Trust, and follow basic rules like staying below 400 feet and always keeping the drone within your visual line of sight. If you're flying for business, the rules, known as Part 107, are much stricter. You must pass a knowledge test to get a remote pilot certificate and register every drone you use. A major new development from the FAA is the Remote ID rule. Think of it as a digital license plate for drones. It requires most drones to broadcast their identification and location information, allowing law enforcement and aviation authorities to see who is flying in their airspace. Across the Atlantic, the European Union Aviation Safety Agency, or EASA, has created a unified set of rules for all member states. Their framework is based on risk. The open category is for low-risk flights that don't need prior authorization but have strict limitations. The specific category is for medium-risk operations that require a pilot to conduct a risk assessment and get approval from their national aviation authority. And the certified category is for high-risk operations, like carrying passengers, where the requirements are as strict as those for manned aviation. The future of this technology is even more mind-boggling, and it's being driven by artificial intelligence. AI is transforming drones from remotely piloted tools into intelligent, autonomous systems. AI-powered drones can navigate through cluttered environments like a dense forest without GPS, using computer vision to map their surroundings in real time. They can make their own decisions, like a drone inspecting a wind turbine that autonomously identifies a crack, takes a series of high-resolution images, and even classifies the type of damage for a report. AI also enables swarm technology, where groups of drones work together cooperatively. Imagine a swarm creating a temporary communications network over a disaster area, or systematically searching a vast wilderness for a missing person. This autonomous future presents the biggest regulatory challenge of all. To manage skies filled with intelligent drone swarms, package delivery drones, and even flying taxis, we need a new kind of air traffic control. This concept is called unmanned traffic management, or UTM. A UTM system will be a digital network that manages the flow of drone traffic, automatically allocating airspace, preventing collisions, and ensuring drones don't fly into restricted areas. It's the key to unlocking true large-scale drone operations, especially for flights beyond visual line of sight, or BVLOS, which is the ultimate goal for industries like logistics and long-range inspection. The journey of the modern drone is a testament to incredible innovation, merging robotics, advanced sensors, and powerful software. But it's also a story about us, about how we as a society choose to manage a powerful new technology. Finding the right balance between fostering innovation and ensuring safety, security, and privacy is the critical task ahead. The next time you see a drone in the sky, remember that you're not just looking at a clever gadget. You're seeing a complex ecosystem of technology and regulation, a glimpse into a future that is already taking flight.